So now we're on part 4 of question 1. This time we have the amount we spend in every month to be xi from x1 to x12, and we want to make sure that with 95% of the time, we have enough money in our bank account so that we can actually spend this much throughout the year. This is assuming we don't earn any money at all, or rather it's a bank account which is only for spending and whatever, right? That's not important. So first of all, let's define a random variable t, which is equal to total amount spent in the year. We know that t is just equal to sigma xi, right? Oops. And look, untidy, whatever, this is fine. All right, yeah, so t is equal to sigma xi. So what can we say about, let's actually go here. Expectation of xi we know to be 1500. Variance of xi we're given to be 500. This whole squared, because the standard deviation is 500, so variance is going to be 500 the whole squared, which is a large number. Annoying. It's annoying to deal with large numbers, but it's like not hard. It's just you might make more mistakes. So now, what is the expectation of t, which is equal to expectation of sigma xi, which from linearity of expectations gives us sigma expectation of xi. Since all the xi's are the same and have the same expectation, this goes from I is equal to 1 to 12. This is equal to 12 times 1500, which is equal to 18,000. Right? Variance of t is equal to variance of sigma xi. And since all the xi's are independent, this is just equal to sigma variance of xi. And just as before, this is equal to 2500 times 12. Right? This is 250,000 times 12, which is 3 million. I'm going to put the commas so you don't get confused with the number of zeros. So now we want enough money in our bank balance so that it covers our expenditure with 95% probability, right? So in this question, let's actually look at deviation from the mean rather than looking at the expenditure in terms of an absolute value. So we want to keep our bank balance such that we deviate from the mean, or we want to keep our bank balance's expectation of t, or the expectation plus epsilon, such that the probability of deviating by more than epsilon is less than 5%. So if we have expectation of t plus epsilon, and the deviation and the probability of deviating by more than epsilon is less than 5%, that means we have enough in our bank account to, well, survive the year, I guess. So we want to find an epsilon such that deviating from the mean by more than epsilon is going to be, the probability of that happening is going to be less than 5%. So let's look at the probability of expenditure of deviating. Oops, that looks weird. We want this. To be less than equal to 0.05, right? Now this, let's actually do a series of inequalities. This is less than equal to probability of t greater than equal to. So if you're trying to bound the probability of t greater than something, then it's definitely going to be bounded by the probability of t greater than equal to that same thing, which is equal to probability of t minus expectation of t. Oops, no absolute value sign yet. Greater than equal to epsilon. So these are the same things. But now let's introduce an absolute value sign by doing this. This is less than equal to probability of t minus expectation of t greater than equal to epsilon. Now I'm adding another situation of expectation of t minus t greater than equal to epsilon. So if I'm adding this situation, because this is a probability is always going to be a non-zero or non-negative quantity, so adding something is always going to make this larger or the same value, right? So now look what I've done. I've added t minus epsilon t, the event that t minus epsilon t is greater than epsilon, and the event that t deviates from below the mean by epsilon, right? And these two together is equal to probability of t, did that again, t minus expectation of t, the absolute value of that deviating by more than epsilon. And now if we bound this by 0.05, if we bound this by 0.05, then obviously this is going to be bounded by 0.05 because we've only had less than equal to signs on the way to this expression. So if we bound something which is greater than this expression by 0.05, then it's going to be good enough. Now let's use Chebyshev's inequality to bound this. Probability of t minus expectation of t greater than equal to epsilon is less than equal to variance of t divided by epsilon squared, which we want to be less than equal to 0.05, right? And this, since variance of t we calculated to be 3 million, this gives us epsilon squared is greater than equal to 3 million over 0.05, which is equal to 20 times 3 million. And when we do some calculation, this just gives us epsilon is going to be greater than equal to 7,746 of sorts. This is an approximate value, just plug that into a calculator or something. And if you have to do this on an exam, leaving that as root 60 million, yeah, 60 million is good enough. So now we have the deviation from the mean should be greater than equal to 7,746, right? So now all we need to do is set our bank balance to be expectation of t plus epsilon, which is 18,000. I think I put an extra 0 there. Plus 7,746, which is equal to 25,746. So this is what you want your bank balance to be, so that you'll have a under 5% chance of going bankrupt at the end of the year.